Good morning, everybody. I'm very glad to present this work made by the teams of University of Pisa, led by Linda Giresini, and University of Cagliari, led by Mauro Sassu. This work is entitled Large-Scale Survey Method for the Integrity of Historical Urban Wall, Application to the Case of Volterra. This work is a part of the work made for the Mike, mitigating of the impact of natural hazard on cultural heritage sites, structure and artifact. In this line, I present the outline. First of all, we will talk about the historical urban wall, highlighting what are the main features, talking about some failure cases happened in Tuscany that induced us to study this topic. And the presentation is essentially focused on the method of survey and a survey form that we developed for the case study of Volterra, a very important case study. And in this sense, we develop a survey form in order to fill a database with the more relevant information in order to do a vulnerability study of this infrastructure. Urban walls are dated back to the Middle Age period in which inhabitants need to protect their city from enemy. Military function is not the only function of this infrastructure because they also add a retaining function in case of complex altimetric development. And in addition, we can talk about spread infrastructure with a prevalent linear development, in some cases complex altimetric and planimetric development, all around the external perimeter of the ancient city center. Talking about the structural feature, we can have, in general, this recurring element. External face, internal face made in masonry with mixed texture, regular in some cases, irregular in other, very various kind of masonry, and internal core made by a filling of earth or masonry with poorer characteristics. In Tuscany, in the last 10 years, happened 7 cases of collapse of historical urban wall in Pistoia, San Gimignano, Volterra, Roccalbegna and Magliano. These are very relevant city centers. In particular, San Gimignano and Volterra are famous all over the world for their historical background. So it's a very important losses that we have in case of collapse. In this table, you can see the date back, the location, the extension of the collapse, and the observed cases of the collapse of these 7 cases in Tuscany. The repairing cost is a very important element in order to estimate the losses. In the case of Magliano in Toscana, we have 300,000 euro of repairing cost, but very important amount in case of Pistoia and Volterra, fourth, 1,500,000 euro. But what are the more recurrent causes of collapse? We see that the presence of moisture is a very important element. This can be induced by rainfall or by other causes, and this element, joined to poor quality of masonry, low maintenance condition, causes collapse, as Emma best explained in next slides.
So in the next few slides, I will be discussing about a few failures events which have happened in the Tuscany region in the last decade. The first example I will be talking about is the one of the Pistoia urban walls, which collapsed partially in September 2011. The collapsed portion is about 50 meters wide and between 7 to 11 meters high. Mainly, the wall is made of a very poor masonry, which is basically composed of polished river stones and a core which is filled with earth. And this is something that all the failures I will be discussing about have in common. So the masonry wall is made by an internal layer, an external layer, and a core which is filled with earth. And as you can see from the pictures, there is huge presence of vegetation on the external layer, which means that there might be huge presence of water behind the masonry wall. And again, this is something which is common for all the failures we will be analyzing. The other example which is shown in this slide is the one of the walls of Magliano in Toscana. The collapse happened in November 2012, and again, the material quality is very weak and is basically rubble masonry again with a earth filling. The other two examples I will be discussing about are the one of Cana di Roccalbegna and San Gimignano. The first collapse involved a section of the walls, which again is a linear section and is set in an urban context, and however is way smaller if compared to the case of Pistoia. The section is indeed just 12.50 meters wide and about 4.60 meters high. After the collapse, cracks were detected on adjacent sections of the walls, and as well as this, as said before, there is huge presence of vegetation as the picture shows. The other example is the one of the walls of San Gimignano, which collapsed without evident warning sign, and this can be due also to the fact that the location of the failure event is far away from the city center. So differently from all the cases we have been discussing about, this section is away from the city center. So again, it caused huge damage, but it didn't involve an urban context. So the last example I will be talking about is the one of Volterra, which is our case study. Volterra was interested by two failure events. The first one happened in January 2014 and the other one in March of the same year. The first section, the section on the left, is a linear section of the wall circuit, whereas the one on the right, which represents the collapse that happened in March 2014, is an angular section. The walls had a retaining function, so basically they retain the soil which is at the back. And after the collapse, the building foundations were left bare. So this means that huge economic losses happen. Damage not only to the wall circuit, but to the buildings which stand on the upstream section as well. And signs of moisture were detected on the walls even before the collapse, so just before and even after it. And this is a sign of the presence of water behind the masonry wall. And as well as this, something that was looked after very carefully is the fact that the gas pipeline could have been damaged by the collapse, and this is something which could have caused even more damage. We will now move on to the method of survey, which is the core of this research work. First of all, in order to do this, we had the necessity to evaluate three boundary conditions, which are the topographical, the hydrogeological, and the structural one. And this information was deduced from the use of a GIS platform together with on-site surveys. The combination of these two methodologies helped to obtain a survey form, which is the result of the work. As you can see from the pictures, we didn't use any difficult or technological technique to perform the on-site surveys, but indeed we used very basic instruments. Moving on to our case study, which is represented by the Volterra urban walls, we will show how the method of survey was developed. First of all, we started with the use of a GIS platform to identify 107 vertical sections. The sections were identified with these three criteria. The first one is that we decided to put one vertex for each angular discontinuity. An additional checkpoint was chosen when the distance between the vertices was greater than 50 meters. And then on-site surveys help to evaluate where additional checkpoints were necessary, together with the presence of interferences. With the word interference, we refer to the presence of infrastructures such as roads, walkways, and any other underground infrastructures, any other typology of infrastructure, or buildings, which can be either public buildings or private buildings. The use of the GIS platform also helped to develop these maps. By the use of the raster dam, it was possible to measure the declivity of the upstream and downstream section and to produce a slope map, as the picture on the right can easily show. Through the information we got from the previous analysis, and we extended the data to all the urban walls path, and we obtained these three graphs. The first two on the left give us an idea about the upstream and downstream slope. Indeed, if we consider the upstream slope, we can observe that the 70% of the section have an inclination which is lower than 10 degrees, whereas if we move to the downstream slope, we see that just the 32% of the sections have an inclination which is lower than 10 degrees, and we have that the 17% of the sections have an inclination which is higher than 20 degrees. And the other parameter that we decided to create in order to evaluate the vulnerability of the sections is the parameter which we called R, which stands for relative height. And we can see from the graph on the right that almost the 3/4 of the sections have a relative height which is between 75 and 100%. So on-site surveys help to identify the main type of sections, and all the sections were indeed connected to 6 main categories, and these categories vary for earth filling, which can be total, partial, or absent, or for the inclination of the faces, both the upstream or downstream face. As well as this, the section can have a lead out, so the presence of it was evaluated through on-site surveys, and there can be the presence of a railing or not. With information and the method we just talked about, we got to the development of the survey form, which is the main task of this research work. The form is divided into 7 main categories, which are given the letters A to G. And together with this, part of the survey is given to pictures, sketches, and on the top to main information such as date of the survey, of the inspection, as well as name of the operators and geographical location and section type. The section can indeed be linear or angular. On the left, we still have a few information about section B, which regards the type of masonry. Indeed, information is required about the type of blocks, type of joints, and whether the operator can assess the presence of an internal core. C refers to the type of railing, which can be masonry or any other material, and not present is to be checked if there is no railing. D regards the presence of vegetation and moisture. which are together in the same category because they both are a sign of the possibility of water being behind the masonry wall. E refers to the presence of drains, so the operator is asked to check whether drains are present or not and whether their efficiency can be assessed. F refers to the type of land and soil, so this information can be deduced from on-site surveys or from GIS data, as well as previous reports, which can be regional reports or previous geological reports. On the right, we have a typical cross-section, and all the information required are given in main geometric data, so the operator is asked to fill that part of the form with the main geometric data, which can be measured on site. The last part of the survey form involves section G, which regards the presence of infrastructures. So the operator has to verify whether on the upstream and downstream sections infrastructure are present or not. So on the left, it is asked to verify whether roads, walkways, or any other kind of underground infrastructures are present. Whether on the right, the issue is to verify whether buildings are present or not. These are divided into private, strategic, or artistic buildings. And for the buildings, the number of floors is required. This because of the fact that through the number of floors, a general overload to be applied to the soil when vulnerability analyses are being conducted can be deduced. Finally, aerial pictures and sketches can be added to the form. So to conclude, this work is a combination of on-site surveys and GIS information, and this is made in order to develop a survey strategy. This strategy was assessed to be way cheaper and more effective if compared to traditional techniques. And the main goal is for the survey to be helpful when it comes to identify the most vulnerable sections. And on those sections, the next step would be to conduct vulnerability analysis, and after that to plan intervention. Future development would be that after those analyses have been developed and concluded, live monitoring techniques and remote control systems would be installed in order to prevent failure scenarios.
Thank you very much for your attention. Volterra also would like to thank you, the Italian Ministry for the Instruction, University and Scientific Research for the economic support furnished to PRIN 2015 MICE project. Thank you.